Hello, I'm Usamah from the University of Leeds, and the title of my project is Machine Learning-Based Intelligent CFD Simulation for Interactive Design Exploration of the Built Environment. So just going through what I'll be presenting, the aims of this project, some work that has been done by researchers in the past, traditional CFD methods, the different ML method I'll be using, such as reduced order modeling, and comparisons between the different reduced order models and how I use GPRs to predict my flow fields. So CFD simulations are notoriously expensive, used later on in the design cycle for anything, in this case, the internals of buildings. And we hope that there could be a way to integrate this earlier on in the design process, where designers could get fast feedback for changing some boundary conditions. So whether that be velocities or whether that would be inlet, outlet positions or walls, etc. And this is like a very broad goal at the end. So for my PhD, we want to be able to take the necessary steps needed for this end goal. So some of the work that's been in the past, it's by Umitani here, where through hundreds of CFD simulations and a Gaussian process regressor, you managed to get a large amount of CFD data. So you can see the drag here, the streamlines and pressure fields. But this took hours and hours to generate, as it was just pure data and nothing else. Following from that, there was some work done on hemodynamics where they tried to model aneurysms, and you can see the circles here as what would be adjusted and the different pressures that were caused in the blood vessels. Now, this was faster, as it used less data, but started using reduced order modeling. And some of the work was interactive design of glass facades. So when you get these nice curved glass buildings and you want to be able to make sure the glass can withstand the stress and the strain, traditionally use finite element methods, but this method would allow you to get real-time feedback for more complex shapes. So again, going back from traditional CFD, creating your model, generating your mesh, solving the equations that you use, whether it be DNS or RAND, and then post-processing to look at the results and adjusting. And as you want to make more and more changes, optimizations, and more fine-tuning, this will take time. So we hope to work towards something that can, once you make some adjustments, get some feedback as fast as possible. So machine learning, the large amount of data in CFD and its pattern recognition, it's very useful. We want to use, but we want to do more than just feed it more and more data for different problems. We want to use different reduced order modeling techniques to try and highlight dominant features from different flow fields or different patterns to then be able to train models much faster and hopefully be more generalizable. And right now for prediction, I am using a Gaussian process regressor, and we hope to move on to more deeper networks into the future. Yeah. So reduced order models, traditionally, as you have a large set of data, you would then project that to something much more lower order. And that generally can capture enough of the flow field to get accurate enough results. So this is a very common flow past the cylinder here. And you can see here, that's the mean of the flow, just the X and Y velocities here. And as you perform the SVD equation, it automatically ranks the data based on the total energy captured. So this U matrix here, the first mode would capture around, say, 60% of the data. And that's what this is shown here. And as you go further along, it captures less percentage of data. So 2, 3, 4, all the way up to 10. It starts capturing less and less and less. But the more of these you use, the more accurate the final model will be. So this is a design of an internals of a building, just simple divider, inlet, outlet. And I just wanted to attempt to use reduced order modeling. This was very early on in my PhD. So inlet and outlet, this was a transient simulation. And as you look at the modes, this is the first, second, third, and fourth. So from before, you can start seeing how the dominant feature here is just this one stream coming from the top inlet here to the outlet. And as you go along, you start seeing smaller and smaller structures. So yeah, so this is just an example of applying it where the ground truth is there using 4 modes here and using 20 modes here. This is out of around 200, I believe. So just by cutting the data down, you can get a reasonably enough accurate flow profile. But a lot of work has already been done in POD, and we wanted to look at FPCA. FPCA is something that follows on from POD and tries to treat the data as a function. So instead of having the regular eigenvectors that POD has, you would have now eigenfunctions. And the idea is that the eigenfunctions can capture more of the data with fewer modes, making it better to train a model on. So from early on in my project, I did some flow past and obstacle. And these are the modes you get from POD and FPCA. You can see they start off kind of similar, but then start varying. And here I plotted the variance of the captured with each mode. So when you look at the first mode, with the blue being FPCA, around 17.5% is captured, but it's 12.5% captured here. And as you go across, the top 4 modes of FPCA capture more variation in the data than similarly it does with POD. So this is an attempt at the recreation of that, where 5 modes of SPCA capture around 70.3% of the data. And just looking at this here, you can kind of see the obstacle and the path here being a little bit more well-defined than with POD here. Okay, moving on to GPRs, another type of statistical machine learning method. And I was using this early on in my project because we wanted to just to see how accurate the predictions can be. So to go for my training data, following this 2D geometry with inlet, outlet, walls, and tables. So small mesh size. This is all 2D right now, with a low velocity as you would usually get when you have ventilation in a room. And I created a 484 simulation. So traditionally, POD is done time dependent, similar with FPCA, but we believe there's no reason why you can't change that to have a different function. So this function would be of the inlet position. It does have a few shortcomings, as you'll see later. Yeah. So to set up the GPR, I have an input data, which is just a matrix of ones and zeros, which represent what the flow data should look like. So those represent the walls, and then this is the corresponding flow field that I should have. I have removed 3 inlet locations. So I have a training set. Okay. So this is before I apply any reduced order modeling. I wanted to see how accurate I could get. And as you can see, when there's some wall interaction here at the bottom, the model really starts to struggle. But as you move further and further away, it gets a lot better once there's less interaction there. It's also important to note that it has no idea what the inlet velocity here looks like. I removed all that, but if I like add 1 or 2 data samples from that, it does improve dramatically. Again, now combining reduced order modeling with this method. So I group the individual data sets based on the inlet location here, and I apply both POD and FPCA separately as a comparison. And I then use those and attempt to predict the dominant modes from both of those in the goal in hoping to reconstruct the original flow field. Yeah. So, okay. I use Scikit FDA for this, and you have to do a lot of work to the data. So originally, if I have 24 sets of data and say the modes are 10,000 long, I have to convert that into one singular vector and then train the model to predict that and then reshape it back to the original. That's the current way of doing it. And again, when you want to choose the number of modes, you look at the variance that's captured. And as you can see from just the FPCA here for this flow field, around 3 modes here, 2 there, and 2 there, 87%, 87%, and 94% is captured. And as you try to use POD, you have to use 15, 12, and 11. So you have to use a lot more data. So this is the eigenfunctions I mentioned earlier. As I'm looking at as I'm looking at a function based on inlet position, I have around the top 5, I think, components here. And as I mentioned before, usually POD and FPCA is on time-dependent data. But as I try to use it for this method, it starts to struggle when I have less and less data for specific positions, such as at the wall. So this is inlet position 2, which is something really low down to the ground, close to a table. So it does well at the beginning, but then it's later on, the other components are less and less accurate. Similarly with position 6, where it has some parts are accurate, but it still has that wall interaction that makes it weaker. Whereas inlet 11 is much higher and has very minimal wall interaction, and that is close to one-to-one perfect. And similarly, to rank the modes, you have to have something called scores, and this assigns each of the functions its own percentage that it use the first function more and the second function less. And as it's FPCA, these are functions. So right now, these are quite large, but there is a goal in the future to make them much smaller. But again, as you go across here, as you move further away from the wall, it starts to fit the ground truth a lot more accurately. And as you try and reconstruct the FPCA, it's again struggling here. It can capture where the inlet is, but that distinct curve isn't there. And it starts doing better as you go further and further away. This is a big graph, but this is what I did before with just POD modes, as I have to use 15 different modes. I have to capture 93% of the variant. I have to use a lot more. So it just shows that the amount of data has increased by a lot. Yeah. So when I'm comparing it with the POD, this is the ground truth and the GPR prediction. So it's struggling a lot more to predict this curve over here. It assumes it's a straight path across. It's you hear the error, whereas the error is a lot higher here. Yep. Yeah, this is just following on from comparing the POD to the FPCA. Yeah, the FPCA is just better showing that curve, but it does struggle against the wall here. And the conclusions, FPCA can capture large variations using less data than POD. GPR can predict the flow fields without any reduced order modeling. But something to note is on a simple laptop that I use, doing it with just the raw data and all the samples takes around 40 minutes. Whereas if I'm doing it using either POD or FPCA, it takes around 30 seconds. So it's significantly faster. In future work, we want to try and use more deeper networks, such as Bayesian networks that can use the GPR for each node. We want to try and couple more information, such as indoor air quality or thermal comfort, something that civil engineers actually use. And I hope to move on to some 3D simulations. So thank you for listening.